Hey, this is Mr. Aiden. I'm back. This is AP Chemistry 2017 AP Chem exam free response problem number 3. We're going to be going through the 2017 AP Chem exam. We've already been through problems number 1 and number 2. So let's get the number 3. Number 3 starts with an equilibrium problem. You can see I have an equilibrium expression here of a reaction of N2 gas plus O2 gas gives me 2 NO or 2 nitrogen monoxide gases. And the first thing they want me to do is my Kp expression. And so for A, my Kp expression is going to be my products. Remember, we're going to do pressure of NO, and that's going to be squared over the pressure of N2 times the pressure of O2 gas. Don't do the brackets for this. We're doing parentheses for this. We're doing partial pressures for your Kp, and that is worth 1 point. Okay, very easy. Equilibrium expression worth 1 point. Then it says a student injects N2 and O2 into a previously evacuated rigid vessel. It's at 2,000 degrees Celsius, and we know the initial partial pressures. As soon as you see initial, what are you going to think of? You're going to think of ice, aren't you? You're going to think of initial change equilibrium. So we have N2, we have O2 in equilibrium with 2NO. So my initial is going to be 6.01 atmospheres. I have 1.61 atmospheres here, and I have 0 initially. And change in equilibrium. Now, they need to give me either something at equilibrium or the total partial pressure at equilibrium. It tells me the partial pressure of equilibrium is 0.122 atmospheres of the NO, which means, remember, the change is working via your molar ratios. So we're looking at our molar ratios for this, which means I increase 0.122 atmospheres here, which means for every 2 NOs we increase, we're going to decrease 1 mole of the O2. So we're taking 0.122, we're dividing by 2, which means we're going down by 0.061, and we're going down by 0.061. So we have 6.01 minus 0.061, and we get 5.949 atmospheres at equilibrium here. We have 1.61 minus 0.061, and we get 1.549 atmospheres here. What are we going to do with these numbers at equilibrium? We're going to put them in our equilibrium expression. So Kp is going to be equal to my 0.122 squared over my 5.949 and 1.549. And so I take 0.122 squared divided by 5.949 divided by 1.549, and I get a Kp of exactly 0.00. And take a look. We have 3 significant digits, 3 significant digits, 3 significant digits. Round to 3 significant digits, 162. And so that is my Kp for this expression. Now, see, this Kp is much less than 1. Which means my reactants are favored, aren't they? My reactants are favored. I barely, 6.01 down to 5.9, 1.61 down to 1.549, we've barely even moved over to my products. And that B was worth 2 points. Number 1, for finding the correct equilibrium partial pressures. So 1 point for this. 1 point for plugging it in my equilibrium expression. Obviously, if you got A wrong, then your Kp might be off, but you might still get that second point because you're at least consistent. Okay. So let's go to E. E, we're going to a little bit more of an acid base, a weak acid base problem. And it says we know that we have HNO2 as a weak acid. We know the Ka of that. We know the pKa of that. How do we find the pKa? The pKa was negative log of my Ka of 3.40. It says a student is asked to make a buffer solution. How do I know what a buffer solution is? It's a weak acid with its conjugate base. So the HNO2 with some NO2 minus. And it says we're going to make a buffer solution of the pH of 3.40 using this 0.100 molar HNO2 and the sodium hydroxide. There is another way to make a buffer, and that is using a titration. Because let's take a look. It says explain why the addition. Why can we do a titration to form a buffer? Well, HNO2 aqueous plus a strong base of hydroxide, what does an acid give away is H plus, which leaves me with H2O and NO2 minus. And do you see how we are forming the NO2 minus? And we also have some HNO2, which makes this a buffer. Now remember, the perfect buffer for a titration is halfway to the equivalence point. That is where our pH is equal to the pKa. And so we have 1 point for a recognition. Believe it or not, there's 2 points here. 1 point for a recognition that you need to have HNO2 and NO2 minus the conjugate base in order to have a buffer. And 1 point for my balance reaction right here, my net ionic reaction. So 2 points for E2. Okay, that's a gimme. And then we have E1. And then E2, it says determine the volume that you would need. Well, you got to get halfway to the equivalence point. So if you have 100 milliliters of 0.1 molar HNO2, the equivalence point would be 100 milliliters of 0.1 molar of NaOH, because it's M1V1 equals M2V2, which means we need exactly 50 milliliters of my 0.1 molar NaOH in order to get halfway to the equivalence point, or where there is a buffer. Okay, so you get 1 point for the correct volume, 1 point, and justifying your answer of 1 point is worth 1 point. Of saying that is halfway to the equivalence point, you are going to convert half of those HNO2s into NO2 minus, and so that is worth 2 points. Okay, let's go to D. D says a student makes a buffer by taking NaNO2. What is NaNO2? That is the NaNO2 minus when I dissolve it in. I have HNO2. What do I have if I have the conjugate base and I have a weak acid? I have a buffer. And so which is more resistant to changes in pH, when a strong acid and strong base are added, or when a buffer is made like this second one? The second one is better. The second one is better. The second one is better. Why is the second one better? It's because when you're doing a titration, you are using moles of the HNO2 to make the NO2 minus. You're not doing that when you're adding a salt. When you add NaNO2 solid directly into the HNO2, you are not losing anything. You still have the maximum moles of the NO2 minus. You have the maximum moles of the HNO2, which means this is better at resisting pHs. You're able to resist acids and bases. Okay, so you get 1 point for that that discussion. Then we go to E. E says a new buffer is made with HNO2 and with some ingredients, and we want to know below what's going on. So let's count up how many HNO2 molecules I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 moles or 10 particles of HNO2. That's my weak acid. Take a look at my NO2 minus. I have 1, 2, 3, 4, 5. I have 5 particles of my NO2 minus. Think about Henderson-Hasselbalch. The Henderson-Hasselbalch equation. pH equals pKa plus the log of your conjugate over your acid. Well, when these are equal, the pH is equal to pK, but you can see how here I have more of my HNO2. I have more of my weak acid, which means the pH is going to be below 3.40 because I have, it's less than, I have more acid in there. Now you could have put in here a 5 to 10 ratio and done your little math there, and you would have found out the pH is less. You can do it either way, but you have to justify your answer somehow. So you can see how this is worth 2 points. Number 1 for saying the pH is below, obviously, and 1 point for your justification of what's going on in this diagram. So this is problem number 3. You can see it's worth 10 points. 1 point for A, 2 points for B. That's up to 3. 4, 5, 6, 7 points. 8 points, 9 points, 10 points. 10-point problem. Make sure you put your score at MrAiden.com. That's the 2017 AP Chem exam, problem number 3. See you tomorrow.